Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to be an introduction into what is known as Gauss's law. So before we talk about Gauss's law, I want everyone to kind of pay attention to this upper right here. Gauss's law is based on the concept of electric flux. So before we get into the video, I want to take a moment and review that. So what we're looking at is, imagine we have an electric field vector somewhere in space. We've got some sort of small area here in the region of that electric field vector. If I define a normal, and again, normal means right angle to the area, and you'll notice I put a hat over it, that means unit normal. The mathematical quantity called the electric flux is equal to the component of this electric field vector that's in the direction of the normal times this cross-sectional area. Now, because that component is adjacent to this angle I called theta, it's equal to E cosine theta. So the flux through this little piece of area here would be EA cosine theta, measured in Newton per Coulomb meter squared. In the language of vectors, we sometimes define what's called the dA vector, which is in the direction of the normal and has a magnitude of area. And then in terms of dot products, the flux through a infinitely small surface would be E dot dA. All right, now over on the left, what we're looking at is we've got this point charge system, and I went ahead and drawn some field lines around that point charge. And what I'm going to do now is I'm going to draw a surface. I'll make it a green surface here, over here somewhere. And it's important to realize this surface is a three-dimensional beast here. So here's a surface I'm going to call S. Now, when you look at this picture, you'll notice, although I don't have one drawn, you can imagine field lines all around this charge. And, one of those field lines is coming along here. At some point, it's going to enter that surface. Now, generally speaking, when a field vector is entering a surface, we say that the flux is negative. But that field line is going to keep going and then leave the surface. So you'll have an outward flux somewhere else. And it's important to realize that if I take this surface, I put it maybe like right here, there's a field line going in, but that field line goes out. Pretty much everywhere I put this surface, that's true. Now you notice I said pretty much. There is a way that I can orient this problem so that there are field lines that leave this surface but never came in to begin with. And that's if I make it so that the charge is inside the surface itself. Now all of these field lines all leave this surface, but they never came in to begin with. So now we have a net positive flux. Gauss's law is about the flux through a closed surface. Now, before I talk about Gauss's law, let me point some things out. Right now, if you actually count, there's 1, 2, 3, 4, 5, 6, 7, 8 field lines going through that surface. Now, that doesn't mean that the total flux to that surface is numerically equal to 8, because the number of field lines you draw in your original picture is somewhat arbitrary. But the 8 is a number that's, I can at least say, is proportional to the number of field lines, at least within this problem. Notice that if I change the orientation of this, these 8 field lines still go through this surface, no matter how I reorient it. As long as that charge is inside of that surface, all 8 field lines go through the green surface. Therefore, the flux is not changing with orientation. Also notice if I make the surface smaller or larger, that does not change the fact that those 8 field lines still go through that surface. The total electric flux of this surface does not depend on its orientation or its size. Now, let me go back to that wording, total electric flux. So imagine we were trying to calculate the flux, right? And again, here's how we calculate flux. So what we would imagine here is breaking this surface up into lots of little pieces, lots of little areas. And at every area, I could draw an electric field vector. Now, in this picture, the electric field vector, let me draw that in, let's say, black. The electric field vector might look something like this. Now, it is not necessarily normal to the surface. In fact, it's probably not. The normal might look something like this. And again, that would be the normal direction. It actually makes a right angle to the surface. Now you'll notice there's an angle between them. I can say that the flux through this little tiny piece is equal to magnitude of the field times the area of this little piece times the cosine of the angle between them. The total electric flux we would get by kind of repeating the process. Do another area, do another area, do another area. Now, I'm not going to worry about actually doing the calculation, but in theory, this is going to come out to some positive value. So the total flux is going to equal the sum of these terms, all the EA cosine thetas, over this entire body. Now, in the language of calculus, we would imagine this infinitely small. The flux through a very tiny piece is a d phi, which is an E dot dA. This is just the, I guess, stronger math way of saying this. The total electric flux we would then get by adding them all up. And in the language of calculus, that means the integral. So the integral E dot dA over the entire surface, and that's what that symbol means, entire, would give the electric flux. Just like over here in kind of an algebraic sense, if I were to break this green surface up into a bunch of little chunks, I could find an electric field at each chunk. I could multiply by the cosine of the angle between the electric field and the normal, then multiply by that small little area there, and then if I sum them up over the entire body, I would get the total electric flux over this surface. Now, remember that the electric field is proportional to the charge making it. So this thing right here, the electric field, whether I'm working with the integral form or this form, this electric field strength is directly proportional to that charge at all points on the surface. So that means that when I finally do these calculations, that total flux is going to be equal to some number that is directly proportional to the charge, meaning equals some constant times the charge. And it's important to realize what charge? The charge inside of this surface. Now, the million-dollar question, well, what is this constant? So I'm going to draw a simple example down here below where I go through a mathematical calculation and try to figure out what that constant is. So imagine now we take a point charge. And I'm going to start with just a positive point charge. And what I'm going to do is I'm going to try to perform that calculation for a geometry that I know about. The easiest type of geometry for me to use here is a circle. So if you give me a moment here to create one. And I shouldn't say circle really. What I'm going to use is a sphere. So imagine a spherical surface. I'm going to go ahead and draw this in green. Important to realize that this surface is a three-dimensional thing here. It's a three-dimensional sphere, so here's like one side of it, and then it comes around like so. So imagine this three-dimensional surface around this point charge. I can draw electric field vectors at all points on the surface. If I come dead away, here's a spot right here where the electric field points this way. I could come down here. Again, here's a spot. You got to imagine it's on the outer surface of this green, the outer green surface here. Electric field would point this way. Maybe I come over here, and again, where it interacts with the surface, electric field's this way. I'm going to think about now this calculation here, this EA cosine theta. Notice that these electric field vectors are all radially outward. Let me draw one more. Radially outward from this charge. I'll draw that right there. These electric field vectors all point dead away from this charge. The angle between the electric field and the normal, if I draw normal vectors here, 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 and here, notice that these normal vectors are all in the same direction as the electric field. So this EA cosine theta, well, the cosine theta part, the theta is 0 and the cosine of 0 is 1. So if I were to use this formulation here, the total flux to this surface is going to be the sum of all the electric field strength times areas times the cosine of 0, which is 1. Now this area, I should maybe put a little I on it because, you know, there's like you got to imagine like a small area here, a small area here, a small area here, and so forth. Now let's think about doing the summation. There's no reason for the electric field here, 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 or here to be the same. As long as we are on this outer surface of this sphere and this charge is centered, then the electric field should be the same, which means on this summation it can come out in front. So this is equal to the electric field times the sum of all the little a sub i's. Now, the electric field we actually have a value for. Because this is created by a point charge, we can write this kq over r squared. And the sum of all the little areas here, if I sum up all the little areas on this green sphere, I'm going to get the area of that green sphere, which is 4 pi r squared. And you'll notice these are going to cancel. So what we get here, and I'm going to group the constants, is 4 pi k times the charge that's inside of this surface. Now, I did this in kind of an algebraic format. You get a very similar, you get exactly the same thing if I write this out in the language of vectors in differential format. I'm just going to leave this video like this for now and not worry about the integral part of it. Again, whether you use this formulation or this formulation, you get 4 pi kq out of it. And now, if we kind of put things together, we have a law that's called Gauss's law, which says this. The total electric flux through any closed surface, which is equal to the sum of all the EA cosine theta terms, and you got to imagine that sum happening over the entire surface, is equal to this expression, 4 pi k times the charge inside the surface. Or in the language of calculus, the integral E dot dA over the entire surface is equal to 4 pi k times the charge inside the surface. So either of these, I use this form in my college physics classes, or this form in a typical calculus-based physics class, but they're conceptually saying the same thing. And Gauss's law, again, it's a law based on electric flux that relates the electric field to the charge inside the surface. Important uses for Gauss's law? Well, electric fields can be very difficult to calculate, especially when the problems get three-dimensional. Gauss's law will give an alternative way to try to figure out what the electric field looks like around various charge distributions. But it can also be used to figure out things like charge or charge densities. It can be used to find both surface and volume charge densities, and linear charge densities for that matter, during the right set of circumstances. So basically it gives us information about either electric fields or how charge is distributed in space are the two main uses. So I hope this video helps at least give you an idea of what Gauss's law is about. I think I'll save the examples for another time. Have a great day.